It turns out that all those observations of the effect, or what quantities or what variables affected the current which is induced in a loop of wire, required Faraday to come up with this concept of magnetic flux. And before I go into the kind of specifics of that, magnetic flux is a measure of the number of magnetic field lines which are piercing a loop of wire. So I'll just put that definition or that description there right at the very beginning. And just a couple of definitions of quantities before we move on. If we have a magnetic field represented by these arrows here, these lines and these arrows, so the magnetic field's going up the page, and if we have a coil of wire, a loop of wire, which is this this kind of circle here at a funny angle, we can kind of think of it as looking side on, and it has an area A. That loop is, if you can kind of think and help me out here, look in 3 dimensions, that this loop of wire is not in the same plane as those arrows that are going up the page. And if we stuck an arrow in the middle of that coil of wire, perpendicular to the plane of that, an arrow in the middle of that loop of wire, and it went up at an angle which is perpendicular to the wire, it would form an angle with the magnetic field. And that line that's coming up there is called the normal to that loop of wire. So I'll write that down there. That's the normal to the loop, to that area. And once you get into higher levels of physics, we can actually show that we define, say, an area as actually a vector, and so it has a direction. And we don't need to worry about that here, but that's kind of why we talk about this stuff and where these equations come from. So we can define something called the flux. Okay, the flux has this symbol phi, and it is measured in units of Webers, and I'll write that down in a minute. The flux is equal to the magnetic field strength multiplied by the area times the cos of the angle between the direction of B and the normal, or the right angle to that loop. Okay, so again, one more time, let's say it together. The flux is measured in Webers. This is a Weber. What a very strange unit. This is the magnetic field strength measured in Tesla. This is the area of the loop measured in meters squared, and this is the angle between the magnetic field direction and the normal to the loop. So what the heck does this flux mean? Well, as I said, flux is a measure of the number of magnetic field lines piercing the loop of wire. So you can think of it like this. The higher the magnetic field, the stronger the magnetic field, the more magnetic field lines are going to be going in some kind of space. Okay, so if you've got more magnetic field, then you've got more magnetic field lines going through the loop. If the area is bigger, that means you can fit more magnetic field lines into that area. So as the area goes up, the flux goes up. And also the angle between the magnetic field lines and the normal to the loop influences how many field lines are going through the loop. So if you had a magnetic field which is normal to the loop, so it's going straight through the loop, and there is a magnetic field, and just to make you feel better that I'm not obsessed with drawing fields into the page, here's a field out of the page. The dots mean we're seeing the tip of the arrowhead pointing towards us, so that means it's coming out of the page. So if the magnetic field is normal to the loop, and I've drawn the loop here with a little dot in the middle to say that the normal is coming out towards us. So if the magnetic field is parallel to the normal, then if you look at this equation over here, if you've got theta being 0, so an angle of 0, cos of 0 is 1. It's at its maximum. So if you've got the magnetic field being parallel to the normal, then you get a maximum flux. If you've got another situation, which you can see down, that I've just drawn down the bottom of the page here, the magnetic field lines are now going to the right, and the loop of wire, it's a bit wonky, is still in the same direction, so its normal is pointing out of the page. In this case, our magnetic field is perpendicular. I'll just write that symbol to the normal. And if theta, so the angle between the normal and the magnetic field is 90 degrees, which is what is when it's perpendicular, cos of 90 degrees is, you guessed it, is 0. So you get 0 or minimum flux. And flux, magnetic flux, is a really important concept when it comes to Faraday's law. It helps us figure out how big the current is going to be, or how big the voltage is going to be, which is induced in a loop of wire. Oh, just before I forget, here is, I've just copied that same equation down the bottom here. There is another quantity which is called flux linkage. And flux linkage, unfortunately, has the same symbol as flux, and it's related very much to flux. But flux linkage is for a situation where we have a coil of wire which has multiple loops all kind of joined together, going round and round and round. So it just has that N. So it's saying that if you've got multiple loops, then you've got more effective flux, if you like. So there is magnetic flux. And now we are poised to describe Faraday's law. Finally.